Okay, let's look at characteristics of any quadratic function um, and the graph of it basically. So it has a vertex, and the vertex usually where the maximum or minimum part of the graph is. That's the coordinate, and usually the maximum minimum value represents the y value. The graph is symmetrical graph, if you remember, right? At the vertex, there is the axis of symmetry that goes through, and if I use this little sketch that I made, if I cut that right to the in the middle, if I would have done this graph this properly, the left hand side would have been the same as right hand side. So if I open up Desmos and go back and look at the y equal to x squared, and doesn't matter what it is, but any function, notice that this is the full symmetrical graph. So, and this line that goes through the vertex, that's called the axis of symmetry, and there is an equation that is associated with that axis of symmetry. Is a vertical line, is always x equals to, is actually the value of the x coordinate of the vertex. That is the equation of the axis of symmetry. So in this case would be x equal to 0. All right, so that's that. And then the part that also is important is domain and range. With the quadratic functions, domain is always all real numbers, but the range is where your maximum minimum value is, depending on what kind of a graph you have. If you have an upside down graph, you're going to have a maximum value because the y will have a maximum value. There's a ceiling to the value of y. But if you have a graph that is, let me just do a quick sketch of a graph that looks like it's upside up regular graph like that. Let's suppose it is, and in this case what you will see is that there is a minimum value right here. So that's the minimum value, and that is the range, depending on if it's upside down or upside up. That's where actually influences what the range will be. All right, so those are the characteristics. And then there's another one that in graphs of quadratic, they always follow this pattern. So let's look at y equal to x squared, and I want to show you using a table of values here. Let's start with -3, -2, 1, -1, 0, 1, 2, 3. Now when you plug numbers in there, you get 9, 4, 1, 0, 1, 4, and 9. Okay, now notice that the x values are being added. So from -3 to -1, you're just adding 1, right? You're just adding 1. So for each x value that you're adding, look what is happening. All right, so and you can go back and forth, right? So look at what's happening between these. So between 9 and 5, that's +5. This is +3, that's +1. Okay, and it just continues. So that means that one is called the method of difference. Basically the pattern in here is that for every x value that you add, you change the y value in a format of 1, 3, 5, and that's the increase. Okay, let me show you on the graph what that means. So let me explain this on this graph right here, because I can draw on it. So from here to here, there's 1 unit for x, and it goes up, and that's 1. Great. When you go again 1 unit for x, but this time between 1 and 4, there is 3 units up. And then you notice that the next one between and again you go 1 unit over, that's 1 unit for x, but you go up 5 unit. So the 1, 3, 5, that is very, and then the next one will be 7. Okay, so 7. So that's why if I put in there 4, you will end up getting 16. And the 16 difference between 16 and 9, this is 7. Okay, so that is the pattern that you always can choose, and based on that pattern you can really come up with the with the a value. That's where your a value comes in. So y equal to x squared is based on 1, 1, 3, 5, 7 that goes up for y values. So these are all y values increase, right? But if it turns out that you have y equal to 2x squared, all of these values, the 1, 3, 5, 7, dot, 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 they're just being multiplied by that a factor in front. So instead of 1 over, 1 up, 1 over 1 up, so let's go back up here. If you go 1 over 1 up, you will go 1 over x, still x is going to go up by 1 unit, but this time you go up 2 because now there's the 2 in front of it. So you don't go 1 over 1, but you go 1 over 2 up, 1 over 6 up instead of 3 up, and then 1 over instead of 5 becomes 10 up. That's why the graph gets skinnier and skinnier. So it's very simple. So this coordinate right here, let me use a blue point. It will be 1 over 2 up, and then 1 over instead of 2 here will be 6 up, and then next one will be 1 over instead of the 3, the 6, that would be 10 up. So it would be 3 and it goes up to 10, and you notice that it just gets skinnier and skinnier. And if I continue this graph, you notice that it will be the same as the other side, pretty much the exact same, because it's symmetric. Okay, so it will be the same in there as well, and then you can actually graph it. And that, okay, now so let's look at x-intercepts and y-intercepts. And in this case, it's very simple. So if I have, let's look at this graph right here. Actually, let's go to Desmos. And all right, so let's look at the graph of y equal to x squared. And in this case, what are my x-intercepts and y-intercepts? Okay, well, x-intercepts is when the graph crosses the x-axis. In this case, it will be 0. And the y-intercept is it crosses the y-axis. And in this case, will be 0 as well. But what if we have graph that is been moved up and down? So for example, what if I have a graph that is x squared and then plus, actually let's do minus 3. All right, here it is. Now what is the y-intercept here? The y-intercept, again, the graph, the y-intercept is minus 3, and that is actually the y-coordinate of the vertex. Okay, so and then algebraically you can set x equal to 0 and you can get minus 3 there. That's great. All right, x-intercepts, that's where the graph crosses the x-axis. In this case, we have 2 of them. Now, you can't know it algebraically exactly, but graphically you can guesstimate where that is, and it's closer to minus 2, and in this case it's same, but they are symmetric again. So these are the x-intercepts. Now, notice that we have 1 x-intercepts, we had 2 x-intercepts. Could we have no x-intercepts? Sure. So let's look at it like that. So x squared this time, let's do plus 4. Sorry, plus 4. The green graph, does it cross the x-axis? No, it does not. It does have only y-intercept, and that's basically it. And how about if it is upside down? Does that matter? Not really. Same idea again. You just make sure, so put a negative in front of x. So that would be minus x squared. And if it is, it's down at the bottom. So plus 2 or plus 4. Let's do plus 4. Okay, it's upside down, but it still goes through the x-axis, and that would be it. There are 2 x-intercepts and 1 y-intercepts. Okay.